So in this lesson, we are going to look at some of the miscellaneous topics in encryption. Encryption in REST, some auth tokens, secure boot, then some of the tools which we use, like secrets manager, S3 encryption, a cloud storage encryption, encryption in REST in different fashions. Those are the things we will discuss, just to make sure that you're aware about this kind of things. It's all fall into the category of what we have discussed so far. Take your breaks if needed, because they are a couple of unrelated topics, and let's get into it. First, let's have a look. Where are we in terms of what we discussed in the very beginning? So we had the cryptography, then we have the rings. This is something we are going to discuss. Probably this is more important than cryptography in terms of security. Inside cryptography, we have discussed hashing, then symmetric, then RSA or asymmetric. Then we have discussed digital signature, signing, TLS, all sorts of things. This is TLS, by the way, not TSL. And we have seen all these things uses this 3 algorithms, different permutations and combinations of these algorithms. We have learned Diffie-Hellman as well, DH, which is kind of similar to RSA, but much more compact. And on top of this, we have discussed SAML and finally OIDC/OAuth. So this is kind of where we are. One of the things we need to understand is that this is exactly like a building. This particular tiles you're seeing, it's like a building. If one collapses, the whole building collapses. It's like a house of cards. If any of this algorithm is compromised, this whole thing is gone. For example, RSA. You cannot have OIDC if RSA is compromised. If digital signature, which is a combination of RSA and hashing, if that is compromised, you can't have SAML or OIDC or pretty much any security using cryptography. So that is one point worth noticing. These are all interdependent and nothing is independent. If one goes, so does the other. Very important point to notice. And this is where we are. We have discussed the cryptography part of it. And this particular lesson, what we are going to do is some of the miscellaneous topics in this particular realm, the cryptography or encryption in general. Mostly we'll be talking about symmetric encryption, which is used in disk, TPM, different cloud services uses different types of encryption and things like that. That'll be one of the topics we are going to discuss next. So before we go further, let's iron out a couple of jargons inside the OIDC OAuth world. The previous session was getting too long, so I had to cut it short after the core concept. One of the major differences or major things we have not discussed is the difference between OIDC, OpenID Connect, and OAuth. The funny thing is that there is no difference. Whatever we have discussed is true for both these two things. In fact, this OIDC is nothing but a subset of OAuth in many different ways. That's why this is more of like always mentioned in pairs. Now we have seen the OAuth token we got, the OAuth token. So we have seen that it is a JWT, JSON Web Token. So the difference between OIDC and OAuth comes from the purpose of this token. Normally, it is an OIDC flow. If this purpose of the token is authorization along with authentication, then that is OAuth. Again, in the case of example of ChatGPT with Google authentication, if you're simply logging on into the ChatGPT like it is doing, it is more like an OIDC. But if you're accessing specific things inside the target, specific resource of the owner, like we did. In the case, we were kind of doing OAuth. In the example we have seen, the Azure example. We are trying to access very specific resources. We have not given the full access to the application. The application couldn't access the full administrative access to that particular account, the target account we have seen. So that is more like OAuth. It is not just authentication, but we are limiting the permission of the token as well. There are a few more differences, especially jargons and all, in terms of spec because OIDC have a different spec or specification. There are a couple of difference, but it doesn't really matter to us. At the end of the day, you can think of both are the same thing. This is used for replacing username and password or single sign-on, because this auth token can be used with multiple providers, multiple targets from a single IDP or identity provider, just like SAML for that matter. So that's the comparison between OIDC and OAuth, more or less the same stuff. Now, a little bit about the auth token itself. So the auth token is nothing but a JSON file or a JSON information, JSON web token, JWT. So what we can do with this token, what is the use of it? So this saves like a API key. You can pass it to call different APIs, REST APIs normally, or it can be used pretty much anywhere where SAML can be used in an HTTP header, or anywhere a username and password is required or authentication is required. So that is the use of token, this particular token. So you can pass it to any authentication system. In our case, we were passing it to the Azure, the target Azure account to call the Azure APIs. So for example, there is a API, say API/v1/resources or something else. This particular API will take a JWT token in the header of the request, for example. It's a post request, and in the header, it takes a JWT token. And if the token is not there or the token is invalid, the whole authentication workflow will get re-triggered. That's how this particular API would have been written. So what this API does when it gets this particular token, it exactly does the same thing as it was doing with the SAML token. It takes the content, take the signature, verifies the signature. We have seen a signature is there inside this token, which is signed by Microsoft, or the ITP, which is trusted by this API. This is the API final target. The whole workflow we've been following and obtained this JWT token to call this API and get this resource. So whenever the JWT token is obtained from this particular API or through the header of this particular API, all it is doing, the server is doing, or the owner is doing, is verifying this particular token. And inside that, as you can see, all the permission, all the assertions, just like the SAML assertions, what the claims, what it is signing, it's all there inside the token. Now, another thing worth comparing right here is the comparison between SAML and OIDC/OAuth. A lot of people say that SAML is obsolete and this is like a superset of SAML. I'm not sure about that, because I have seen SAML even today used in a lot of scenarios, especially in corporate network. But the main difference, if you look at SAML and OIDC/OAuth, is that OIDC is designed to work on a lot of other scenarios, much bigger scale, while SAML is designed to work majorly in corporate scenarios. One of the main differences is that this has inherent support for different workflows. For example, you might have seen single page application, web, native application. A lot of authentication scenarios is supported by OIDC. On the other hand, SAML inherently involves an HTTP redirect. Remember when we were getting the SAML token, if you want to refer the session, there was an HTTP redirect to the IDP 302. If you don't have the username and password, or the username and password provided, if the SAML token is not given to the target resource, it always redirect 301 or 302. One of the redirect HTTP traffic is generated by the target server. That is not always the case with OIDC, because OIDC is designed to work with REST APIs. For REST APIs, redirect is just like any other error code, like 404 or anything other than 200. So that way, it is not wrong to say that OIDC or OAuth is kind of a superset of SAML. Whatever SAML normally care to accommodate, it can be accommodated using this particular flow as well. But one thing to note here is that because of that reason itself, there is a lot of attacks against OAuth and OIDC because it supports a lot of scenarios. Rogue clients. For example, there is an element of trust Microsoft is doing with that application we have seen, that small application. It is not a signed application. It can be a rogue application, but it is trying to get permission into my account. If you have looked at, it is a pretty scary thing. That app was not even running on HTTP. It was running on my local host. Even if it is running on a proper server with HTTPS, still there is a level of trust which is being given by Microsoft to that application by pretty much knowing nothing about that application. And with a few simple clicks, it is stealing my credentials. At the end of the day, my Azure credentials. For example, right now, if I'm trying to access that application, nothing is being asked. It already gets the access token in my account. So that kind of trust issues are there with OIDC. But SAML, it's more strict because mostly used in corporate environments. You already know the application. There is no strange application from out wild is there in the SAML workflow normally. I don't want to get into much of a detail, but one thing I would like to do is to have a look at the different flow of these OIDC and OAuth. So I'm going to Google and search for OIDC OAuth flows, and pretty much a lot of this documentation more or less the same thing. I'm going to go to the Okta. Okta is just like the Android. They provide implementation of OIDC, OAuth, SAML, and all sorts of things. Okta, ForgeRock, Ping, Auth0, all these guys are different identity providers, custom identity providers, just like the one we have seen in the Microsoft Azure. So this is the page I'm looking at right now. As you can see, there are so many flows they're going to mention in this particular page. If you are curious about what we've been discussing, feel free to read through one of these pages. This is the page which I'm looking at right now. So different jargons and different details have been provided. Probably it worth its own training. Different flows it supports, as you can see here. Type of the app, server side or web application, single page application, native application. Single page application is, for example, like the WhatsApp web is a single page application. More like native application. They call REST APIs behind the scenes. They doesn't change the web page. It's fully JavaScript running in a single page. Native application, very similar to single page application. They doesn't do HTTP redirect. There is no HTTP redirect inside the single page application. If you have any confusion on what is HTTP redirect, feel free to refer to my networking training. Basically, when you try to access a web page, say for example google.com, the web page or the server redirects you to a different page. One of the most important things with HTTP redirect is the fact that it happens from the client. Servers simply respond with a 301 error code, and it is the client which is making you redirect. A lot of people think that it is happening in the server because it's very transparent when you access it from a web browser, but it is happening from the web browser. Feel free to refer to my networking training for the details. But there is no HTTP redirect in a single page or native application. Very important point. This is trusted application, and there is a service where there is no users. So they are recommending different types of workflows in different types of application. So this is the implementation with auth code with PKCE. PKCE is nothing but an additional verification which is being done to make sure that you are talking to the same guy all over again. Not going into the details, but this is kind of the flow we have seen before. So different flows are there based on the different types of the client. That is what this particular page, very detailed, explaining the difference between these flows and the implications between them, worth its own training. If you have questions, feel free to ask me. I can answer your doubts, or I may plan another training on these topics if there is enough interest. Another encryption topic worth mentioning here before we move on is encryption in rest. Encryption at rest uses always symmetric encryption. So you have a key and you encrypt the data in the disk. For example, you're saving a file to your disk. The idea is that whoever is having access to the disk doesn't have access to the data. So that's the idea of encryption at rest. So for example, you have a laptop. This is your laptop. And the laptop has a disk inside. Say for example, it's an SSD or normal disk, doesn't matter. All your data goes into this particular disk right here. All your local information. Now, your laptop is stolen. Someone has taken that device. He has access to the disk. Now, if the information in this disk is not encrypted, he can simply access it. He can take this particular thing out and plug it into a different laptop or a computer, and he can access all your files. He doesn't need your username or password of this particular device. If your disk is not encrypted, that's what happens. All your data is lost. And more than often in a corporate scenario, your data is more important than this device. What is there inside this is more important, more valuable. Your bank account details, your secret files, your corporate data is within this disk, which is always more important than this particular device. So that's where the disk encryption comes into the picture. So you'll have a single key, encryption key, and you encrypt all the information within this particular drive. Now the question is, where do you keep this key? You can't keep this key inside this disk. Why? Because if someone is obtaining this particular disk, he will obtain the key as well. So we need to keep the key somewhere else. Where is that else? Where else we keep the key? We can't keep it in the disk. Can we keep it in computer memory? No, we can't. Why? Because computer memory goes off when you turn off the laptop. All your data will get lost. You encrypted your disk and you lost your key. This whole thing will get lost. So what to do? Where do you keep the key? So that's where the TPM comes into the picture, or Trusted Platform Module. It is a chip separate from the disk. Within the laptop, mostly within the CPU, you have a module like floating point operation, memory management unit. You have a Trusted Platform Module inside the CPU. And in that, you keep the key secretly of this particular encryption. Now, if someone takes this thing, he don't have access to the TPM. TPM cannot be accessed like that. It's an electronically secure device. So these days, operating system uses TPM for encrypting the disk and to keep the symmetric encryption key inside the TPM. For example, Windows 11 uses TPM. I'm pretty sure this laptop has a TPM. Let's have a look if it has a TPM. So I'm in my device manager of my Windows laptop right here, and there should be something called security devices, Trusted Platform Module. This particular module is responsible for keeping the keys. Also, it supports something called secure boot. We can discuss that quickly, not in detail, but this is the TPM. So for operating system like Windows, this is a essential device. Without TPM, this particular device doesn't boot. So I'll quickly discuss secure boot now that we are discussing about TPM. So TPM is used for another purpose, which is secure boot. So boot, this is a process of starting a computer. When you press your power button of a computer, your laptop or your server, what happens is called boot sequence, booting the machine. So what's the process going behind the scenes is nothing but you have your CPU and you have your computer memory, so CPU and memory, and then disk and other devices. Disk is what matters here, disk. Now the boot is a process of using CPU and memory and loading the operating system, the most important part of the operating system at least, to the memory and start executing and loading different things, including different application into the memory and execute using CPU. Basically reading the disk, different parts of disk, and loading to the memory, mainly the OS. After the boot sequence is complete, what will the memory has? The memory will have the operating system and essential applications, apps. Not all the application, but essential application will be there. For example, the Explorer start menu of Windows along with the operating system. So that is what happens in the boot process. Now, secure boot is all about making sure that whatever we are copying from this particular disk is something we have tested and trusted. What if there is a malware loading into this memory while booting? The whole system will be compromised. The data will get compromised. Someone has kept a malware in the boot sequence. The first program you load is a malware because someone has replaced your bootloader. Bootloader is the first program we run as part of the boot sequence. But someone has replaced it. Replaced with what? With a malware. So he can extract your data. Now what to do with that? Can we do anything? Yes, we can do something. That's where TPM comes into the picture again. TPM. So what TPM does is that it verifies the signature of the code which is loaded into the memory. So there is a binary which is going to sit here. Let's draw that in a different color. There's a specific binary inside the disk. So this is a disk. There's a specific binary. And that binary has a signature. Let's draw that signature in a different color. So this is a signature signed by a specific entity. So there is a private key signature. We have learned about code signing. Just like any other document signing, there is this data here and there's a signature. Now any tampering of this particular code, including malware or any instruction, even if it is a single byte change, that will be invalidating this particular signature. Now that signature is being checked by TPM. It'll decrypt using a public key and making sure that there is no tampering has been done. Then only the OS will load, making sure that the base of the operating system is clean. No one has tampered with the base of the operating system, which is very important because once the base is strong, what I'm going to discuss next or the rest of the training is going to make sense to you, because the entire integrity of the operating system can be built from that base operating system code. All the rings of protection, all the processes, all the application processes, everything can be verified. But if the operating system itself is corrupted, for example, there is a malware in the boot sequence, nothing is secure after that, because malware is running as the operating system with high privilege in ring 0. We have not discussed the ring, but this may make more sense to you after watching the rest of the training actually. But at the end of the day, the whole point is making sure that the base, the first code you are going to run in a computer, when you press the start button of that computer, is trusted and verified and not tampered with. Very important. That is secure boot. At least one of the major part of the secure boot. There are a lot more other things like bootloader, anti-malware and things like that. We are not going to discuss that. But all in all, secure boot is mostly about verifying the code which is being loaded into the hardware. As part of the secure boot, you need to hash and make sure that your hardware is also not modified. CPU, memory, disk, all these hardware modules are also intact. What if someone replaces something like memory, disk, CPU? Then also the secure boot will fail. Depends on how it has been configured. So there is a hash for this. There's a verification for this, just like the verification is there for the code. There is verification for the hardware itself. So the whole thing is verified before loading and start executing things. That is secure boot. And we use cryptography for that. Encryption and signature. That is what all this is about. Before we conclude, we would like to look into a couple of miscellaneous things in the cloud account. So we are going into the console of AWS. So one of the things I would like to show is the secrets manager. We have seen a couple of other things. I am certificate authority, certificate manager, etc. in the previous sessions. Even I am, all these things we have explained. Secret manager is one of the things I would like to discuss. Again, encrypting username and password and things like that. So the idea here is keep some secret or key or username or password. That's what we generally call secret, in a secure manner, in an encrypted manner. So what is the encryption we will be using? we'll be using symmetric encryption. So we won't be dealing with any key or anything like that. So Amazon RDS database credentials, which is a username and password. So how we are handling the key, encryption key, is handled by KMS, Key Management Service, KMS. So KMS is a key management service AWS is having. We can use that for encrypting this particular secret we are giving. So we have different types of secrets here, credentials, mostly credentials. Other type of secrets like OAuth token. We have seen OAuth token, API key, and other things. Pretty much any text you can keep it like this. I'm not going to create a secret. It's pretty trivial. And how do you access the secret? So secret is just like any other object in AWS. Once it is created, you can create IAM roles to assume and access the secret. So this is a mechanism to save secrets in databases instead of plain text. Basically, at the end of the day, a fancy way of encryption in REST. That's what secret is all about, with a lot of other convenience and stuff like that. So we can configure a rotation so that the secret will get rotated. A lot of the passwords and things has to be rotated in a periodic way for security reasons. So now KMS, Key Management Service. Like I mentioned, KMS is all about saving and creating a key securely. And this key can be used for a lot of other purposes. So we have two options, symmetric and asymmetric, which is a public and private key pair. You can use it for encryption as well as decryption. So the other option is verification. Let's see the option for the key. We have seen the verification part as well. Most of these kind of things in almost any cloud provider or any other on-prem or any software tool should be familiar to you by now, or you should be able to easily understand what it is because we have covered all the basics required. So cloud HSM, probably we have not discussed HSM. So basically they are nothing but hardware services for managing the key. They are basically like TPM we have discussed. We keep the key ultimately in a hardware. So cloud providers give HSM to keep important keys, hardware security module, HSM, which is nothing but TPM we have already discussed. We are not going to keep in any computer memory or anywhere else these keys. So we keep in HSMs. So most of the root keys, which all the other keys are encrypted, normally it's best practice to keep in hardware security modules. So these modules, what it does is they keep the key and avoid keep keys in any other hardware devices, like disk, for example. Otherwise, there is always a chicken egg problem when you encrypt a disk. Now you have encrypted a disk where you will keep the key. Unless someone remembers a password or username, which is difficult in the case of services accessing the disk. There's no human intervention. The key has to be kept somewhere safe in a non-hard disk device. That's where the HSM comes into the picture. Different places to keep the keys and things like that. It's all different permutations and combinations of managing the key and things like that. If you have any questions on any of this kind of software, not just AWS, any other cloud provider, feel free to ask in the description of the chapter which you're watching right now, or just ask me question through email if you have any doubts in any of the things. Now, if you look at S3, you will see some encryption options, S3. So Amazon S3 buckets, just like any other storage, it's an object storage, not much different from our perspective. So if you go to any bucket in the properties, you will see encryption. So encryption type, server-side encryption with S3 managed keys, which means that Amazon manages the key and the data is encrypted. So if you click on edit, you will see different options. Server-side encryption with AWS key management service. So we'll be using KMS to manage the key. Then there is dual layer server-side encryption. You can mention your custom key to encrypt the data. A lot of different types of options. Who keeps the key at the end of the day? How much trust you have? How much important the data you're keeping? At the end of the day, you're keeping the data inside the cloud. So definitely it's a good practice to encrypt that data. So that's all I wanted to discuss about encryption, the miscellaneous topics around encryption. In case if you have questions, like I mentioned, feel free to ask through any means, email or the forum or any other means. You can reach out to me and ask more questions. So to conclude, we have looked at a couple of different miscellaneous encryption topic. We have seen secure boot, encryption in transit, and a couple of details on the auth token and things like that. Being said that, I would like to conclude chapter 1 or the section 1 or the pillar 1 of this particular training. So the encryption part, we have seen a lot of details on the encryption, and we are going to start chapter 2, which is the local security. Local security is much more complicated than the encryption, and many times that details are not required. I'll mention this again when I start the chapter 2. So feel free to skip chapter 2 altogether of this training if you're not interested. So chapter 2 is a completely optional thing in this particular training. So we'll start chapter 2 shortly. Thank you for watching. I'll see you in the next.